What is up, developers? Welcome back to the Planets tutorial. Today we're going to finish the Planets project by implementing the eccentricity slider and Kepler's law of orbit ratios. So let's get into it. So let's go ahead to the main.storyboard and under view controller, go ahead and look for the slider and add it to the top left or wherever you want, and set the maximum to something very close to 1 but not 1. Interesting. Next, to add a text field and a label. That's just for looks. Next, open up a new tab and close the right sidebar for more space and open the view controller. Find the horizontal slider, hold down Control and drag to the bottom to add the action. We'll call it the just slider value. Slider value did change. And change the sender to NS slider. We'll be able to access the value with sender.float value. So let's make that a variable. And we need to be able to access the game scene method for changing the eccentricity. So we need to have the game scene too. Up here, make a var, call it game scene, and it's a game scene. And I'm just going to force and wrap all this stuff equals the scene as game scene. And that should probably do it. Let's build. And before I close this on the left, I'm going to add the output, just so we can see what the eccentricity value is while we're running the app. And we'll call it the eccentricity value field. And here we could set eccentricity value field dot just float value, and then we'll do new eccentricity. And now we can close this and run and see here. So great, the value is updating, and I don't want to find out what happens when it goes to 1 because I don't think the ellipse can be defined, because remember the radius formula, and what happens when the cosine becomes -1, then we'll get a 0 in the denominator and the orbit. So anyways, let's go to the game scene and make a new function. Got a little head here. New eccentricity, and takes in a float. We want to set the variable eccentricity equal to that new eccentricity, and also add nodes. Let's go to the view controller and call that, and you'll see the problem that occurs. So do scene, game scene dot new eccentricity, new eccentricity. All right, let's change it. And you'll see that we're adding the nodes. Let's make a new function. Let's call it refresh nodes. Reposition the sun. So sun.position. We can just copy this code right here actually. And let's see what that does after we change add nodes to refresh nodes here. So the sun's moving, and the Earth seems to be getting a little carried away. I think that's because the ellipse is not updating properly. Do path remove from parent, and path equals make orbit path self and eccentricity. Let's see what that does. Oh no. So under move planet, we have removed the path, but I guess we were calling move planet after it didn't exist anymore. So we do that, making path optional. So path, if path is not equal to nil, then we can run. Oh no, I have to deal with unwrapping optionals here. Probably want to just put that in here. And then we can force unwrap these. And run. Alright, let's test this out. Okay, it's still happening. Gotta add the child. Probably that's the problem. Let's try this out. Force unwrap. Do a lot of that. Alright, let's test this out. And great, it is working. So we have set up the eccentricity slider. Let's move on and figure out how to make Kepler's law work. Because as you can see, our planet is booking it wherever it is, and that is not realistic. We want to implement this somehow in code. This A1 over T1 is equal to A2 over T2. So how will we do that? Alright, so what we need is a variable called wedge times, which will be float. And so we will use that to interpolate the rate. So I will make a new function called interpolate rate and add a resolution. Like, how many wedges do we want? Well, let's just say 50 for now. Our increment is equal to float.pi times 2 over resolution. We have like an array full of our area 1s. Now, how are we going to use the formula to figure out the time? Well, we can just say that T1 is like whatever we want, and T2 is what we need to find. So the way we do this is an array of ratios. Because if we have an array of ratios, then we can sort of figure out what the time is. I in resolution. We want to do this, we want to get another variable. And we are using similar syntax. I'm just going to copy paste. And say wedges equals areas 0 over areas I. And this gets us a ratio between the very first area and an area anywhere, and we'll have like a bunch of wedges to deal with. And this is good. Now, what is the problem here, though? Wedges I, of course. Now, finally, we just set wedge times equal to wedges. Now, let's make the interpolation function work for us. We want to get the angular velocity. So let's call it get angular velocity. And what do we want? We want to get it at a particular angle. It can be a float. You need to make sure that we're in range. We don't want to go out of range. So I'm just going to copy some code, and you'll see what I mean. So here's the code, and what we return the float of the. So we also need to bring the resolution back here too, and it has to be the same. So, I mean, ideally, I should just make this a variable. And this is what I mean by being out of range. So, like, I want to index into these wedge times so that I can get what will be my time in the end. I'm dividing the wedge time, so that's a ratio. That's the ratio I use to get that second time. I divide that by the wedge times, but I need to make sure I'm in the array, the range of the array, so I need to truncate the current angle. Let's implement this get angular velocity function. Let's go to didMove, or actually add nodes. Here at the end, I'm just going to interpolate the rate. I'm also going to interpolate the rate when we refresh the nodes. And I want to go to move planet. And here's where I want to get the angular velocity. So we'll say let angular velocity equal get angular velocity at planet.theta. Planet.theta should be time change times the angular velocity. Alright, so it's moving very slow. And change the time change. Alright, I think it's working. Now, like before, I said it was booking it everywhere. But now it's only booking it when it's close to the sun. And that is exactly the behavior we expect. And it's going so fast you can't even tell that we're using a few tricks to simulate Kepler's law. So what if I change the interpolation resolution to 3? Would we then notice those steps in speed? Well, now that is really weird. Yeah, you can kind of see the effects of this technique we're using. You see, it's sort of like if you ever play Mario Kart and you go on the rainbow strips, then you speed up abruptly, and that's what this planet looks like it's doing. What if we have a higher resolution? Well, then you'll not really be able to notice these jumps in speed. Put it up to 100, and I doubt you'd be able to tell. It's getting really slow out there. What if it's a circle? Well, yeah, what if it's very eccentric? That was all for this video. Thank you so much for watching. Leave a like, subscribe, leave a dislike, let me know what I can change. Nobody will see it on YouTube anyways, because they're hidden, but that's all for this episode. Later.